Hello, everyone. Today is my great pleasure to introduce Professor Herman Verlinde as today's colloquium speaker and also as a panel scholar. So before introducing Herman, let me first briefly introduce the panel scholar program. This program has been established in memory of Professor Stan Hanna, who was an eminent nuclear physicist in our department. One of the things Stan found most stimulating was to spend extensive visits to other institutions, having exciting discussions with new people. And that's in recognition of this, his son, David, and David's wife, Robbie, endowed the Hanna Visiting Professor Program to enable our department to bring eminent physicists to Stanford for an extended period of time. So, and this year, we are really glad to have Professor Herman Verlinde as our panel scholar. Herman did his PhD in the University of Utrecht in 1988 with Professor Tuchel. And after postdoc at Princeton, from 1988 to 1990, he joined the Princeton University faculty. And in 1994, he is a fellow of Dutch Royal Academy of Science. And from 1995 to 1998, he is a professor in the University of Amsterdam. After that, he moved back to Princeton, where he is currently the class of 1909 professor of physics. And he's also the chair of the physics department at Princeton since 2017.
And no longer now.
Not anymore?
No, done with it.
Herman is a faculty fellow at the PGTS, the Princeton Center for Theoretical Science, and he was the IBM Einstein Fellow at the Institute for Advanced Study from 2008 to 2009, and he was also a David and Lucille Packard Fellow in 1993. So Herman has made a significant contribution to many fields of theoretical physics, including string theory, conformal field theory, quantum gravity. If you work in these fields, the chances you have learned about many different works of Herman. For example, he made foundational contributions to string perturbation theory, matrix description of strings, warp compactification, and supersymmetric breaking. So in the CFP, he developed the holographic normalization group, the way we understand how to extract gravitational physics from conformal field theory. And he works on quantum black holes, include the statements of black hole complementarity and identification of scrambling time and the mechanical behavior of black hole horizon, and the use of quantum error correction for construction of the black hole interior. Sorry, I don't want to occupy too long time of the talk, so I will give the floor to Herman. Today he will tell us about chaotic quantum dynamics and the quantum geometry of spacetime.
Okay, well, yeah, it's a pleasure to be here. I want to thank again Sir Lang for the generous introduction and also for the invitation to spend a number of weeks here. I should say that Stanford is one of the favorite places for me to visit, also where I usually learn the most from talking to people. And many of the things I'll be discussing today indeed have had contributions from people here, and also my own work has sort of been influenced by conversations with people here. So what I'm going to do today, indeed, I'll talk about physics that indeed has been explored indeed by people here, indeed the connection between quantum chaotic dynamics and quantum geometry of space-time. I'll hope to explain during the talk, of course, what the connection is, but indeed, as I said, people from here have made contributions to it. And in particular, this quantum geometry of space-time, there I would say I'll give you my own perspective. And towards the end of the talk, I'll talk about some new things, but at the beginning will be sort of more of introduction. So here's the outline. Indeed, in the beginning of my talk, I'll talk about the motivations. What are the big questions that we're trying to answer? Again, my field is quantum gravity, or starting out indeed more as string theory. And of course, there are many questions that sort of we're trying to address. But I think it's still useful for me to eventually sort of give you my perspective on what we're trying to investigate and which questions we're trying to answer. In the second part of my talk, which is sort of where sort of things get more specific, indeed I'll talk about the connection between aspects of black holes and this problem of quantum chaos. And in particular, there's this model which is known as the SYK model, which for the last 10 years sort of has provided important insights into sort of aspects on both sides in terms of quantum chaos and also in terms of what black holes mean and how the connection works. And then the last part of the talk, I'll talk about sort of a new direction, which I've been started to explore, and also in discussions with people here, in particular Lenny Susskind, of actually sort of where we want to push sort of the whole idea of connections between quantum mechanics and gravity in a new direction, where we're starting to think about more cosmological questions, and that has to do indeed with the Sitter space. And then I'll conclude. Again, the beginning part of the talk is sort of more like setting the stage. I'll try to go not too fast, but at the same time I don't want to necessarily lose too much time so that we have time for the second part of the talk. So again, so what are the big questions? Of course, if we do quantum gravity, we're trying to address sort of what sort of is one of the remaining questions in physics. Again, we know that the standard model of particle physics works remarkably well. We know that Einstein's theory of general relativity works remarkably well. And indeed, since sort of 25 years, we kind of know quite a lot about the matter content of the universe. Let's see if my pointer works yet. And indeed, if we take the matter content, we take Einstein's equation, and we take the standard model, we essentially can describe physics very accurately over an enormous range of scales, where indeed we go to the shortest distance scales in the experimental setups of, say, the LHC experiment. We can go to cosmological scales, where we're looking at the microwave background and think about sort of the fluctuations that led to it. And nowadays, even, again, we know about the existence of dark energy and of black holes. And we can test our theories there. And again, this framework basically works. Nonetheless, there are going to be important questions that sort of are left unanswered. According to the standard sort of at least way in which we fit things together, we hope to be able to invent a theory that will complete the standard model. And the standard model is based on quantum field theory. Quantum field theory is an enormously successful theory. It can compute things to very high orders of accuracy, and it's been tested by experiment. But nonetheless, again, if we want to include gravity, it's clear we have to do something sort of more than just talking about quantum fields, because including gravity requires new ingredients. And since quite a while already, string theory is viewed as sort of the most promising framework for giving that complete theory. And in the case of string theory, the way this works is that the parameters of the standard model indeed are going to be parameterized geometrically. And then indeed we have sort of this framework, this paradigm where string theory, although it starts in higher dimensions, quickly at least should end up in a setting where we're in 4 dimensions with an extra dimension that has a complex space, this geometry, that will then parameterize things in a way that should match with the space of quantum field theories, but not all of them. The idea is that there should be a theory that connects with our standard model. There may be other theories that could potentially be plausible, and that we call the landscape of possible theories that follow out of string theory. But there may be very many quantum field theories that in fact are not allowed from the point of view of string theory, because they would not be able to connect with the theory of gravity. And this is sort of a program where you can say, hey, from this point of view, what we're trying to do in string theory is what you could call a UV completion, where you sort of add more information that describes the Planck scale physics that corresponds to gravity, but we're sort of maintaining all of the virtues of quantum field theory, and it's sort of an extra sort of detail that we're going to add from the point of view of string theory. However, at least the perspective that I'm going to take in this talk is sort of coming from another angle. I'm not going to be thinking too much from this point of view of sort of starting with quantum field theory. I do want to start from quantum mechanics. These days, again, we have many kind of experimental, of course, verification of that quantum mechanics is the way the world works. In particular, nowadays, indeed, we're thinking about things like quantum devices, where indeed the rules of quantum mechanics really kind of bring us into a new realm. And the rules of quantum mechanics are the things that I want to sort of keep. But at the same time, I want to start asking questions precisely that connect with this current development where we're thinking about, say, quantum computing and quantum information. And that development sort of starts by asking a different kind of question that perhaps one wouldn't immediately want to ask. But indeed, if you do, you get sort of some interesting answers where you start talking about the entropy of the universe. And indeed, once you start thinking about the entropy of the universe, you start organizing things a little bit differently than I just described. So in the universe, of course, we have many different particles, and we have many different objects. And you can basically start counting the amount of, and I would call it information, basically the number of microstates that you can associate with the various components of the universe. And indeed, for most things that we can kind of see and identify, if you look at the numbers, I'm not sure if my pointer is doing what I want it to do. Let's give it one more try. Maybe I should be on that side. That could be it. So, does it come back? It went away. Anyway, I'll do it without the pointer. You can see at least that most of the components of the universe, if you add them up, add to a number of an entropy, a large number, close to 10 to the 90. But if you think about what makes up the information, which is basically what entropy is in the universe, somewhat surprisingly perhaps for people who haven't sort of heard this before, is that the thing that contains most information in the universe, the most entropy in the universe, are things like black holes. And the number that comes out there, at least if you put it in the column over there, is 10 to the 104, which is indeed quite a bit bigger than 10 to the 90. So how do we know that this is actually the case? Because a black hole at the same time is actually a very boring object. It's just, it has no hair. It can form indeed from gravitational collapse. If you look at it, it can rotate. It can potentially have charge. But those are the only parameters, and therefore it would, in principle, have very little information. And it was about sort of a little bit over 50 years ago that John Wheeler asked his student, Jacob Bekenstein, okay, what happens now if I indeed throw something into a black hole? It seems like I'm reducing the amount of information because it becomes like part of this very round and sort of featureless object. At the same time, the second law of thermodynamics should tell me that entropy has to increase. And Bekenstein came back with this surprising answer that basically the entropy of a black hole is proportional to its area. And that became more accurate in subsequent work by, now I cannot even do my slides.
Sorry, I just put it there. Can you try it again?
Let's see if it works. Oh, there it is. Okay. Let's give it a shot. I'm not going to move too far away from the laptop. Maybe that will work. By the way, so indeed, basically, right now, today, almost up to the day, March 1st, 1974, that's 50 years ago, Hawking indeed published this paper in Nature. It was called Black Hole Explosions, where for the first time he actually made this discovery, or announced this discovery, that black holes actually have a temperature. And again, this formula indeed is longer ago from today than this paper was written since the sort of inception of quantum mechanics. And it's a remarkable result. So basically, a black hole indeed has a mass. Once it has a mass, it creates this region of space-time that we call the horizon. If you're behind the horizon, you cannot escape. But remarkably, in quantum mechanics, particles do escape from a black hole. And they give rise to indeed a temperature that Hawking correctly identified. Here I'm using it indeed with all the units in it. Central charge, there's not central charge, the speed of light. And h bar and the Newton constant. And then this formula predicts essentially that a black hole has an entropy that follows from the rules of thermodynamics from the formula of the temperature. And that relationship, if you now apply it to all the black holes in our universe, essentially leads to this prediction that there's more entropy in the black holes than all the rest, basically, of the visible things that we can see. This development of that Hawking sort of discovered this temperature was part of a more broader development that Hawking also made major contributions to, which we call black hole thermodynamics, where indeed essentially it was already discovered that the black hole's area can only increase in any process that you sort of can think of, and it was already sort of called the second law of thermodynamics, of black hole thermodynamics, that area always increases. And indeed, the two things literally become identified at the moment that indeed you make this identification between area and entropy. And of course, at the time it was sort of an analogy, but since then we've kind of learned that these are really fundamental identifications, and that indeed we can start thinking about black holes as made out of real stuff. And if we do that, then we should be able to explain that if we apply the laws of thermodynamics to that real stuff, that basically things that seemingly only follow from gravity, because indeed if we look at the equation here on the left, namely that the change in the mass of a black hole translates to a change in its entropy, in its area, should be thought of as a thermodynamic relationship between energy and entropy. And you can think maybe as the arrow of implication going from the left to the right. But an idea which has become sort of a rather important one, if we go from the right to the left, then this sort of tells you that gravity could be a consequence potentially of thinking about entropy. So from that point of view, at least we now sort of have more confidence in this kind of picture because of something that's called the ADS-CFT correspondence. I will not sort of explain where it was coming from. It came from string theory, but indeed it sort of has provided us with this theoretical laboratory where we can test these ideas in much more detail. So ADS-CFT, ADS stands for anti-de Sitter, which is telling you that we're talking about a space-time that has constant negative curvature. But then if you take a space-time with constant negative curvature, it actually has a boundary. And that boundary is where we could imagine sort of putting a quantum system. Okay, I have to go back here. Let's go back here. And we put a quantum system which is called a CFT, a conformal field theory. And in that case, we can have sort of basically a box in which gravity is working inside of the what we call the bulk. But on the boundary, we have a quantum system where we can actually account for all the degrees of freedom. From the point of view of the right figure, the boundary, and when you go into the bulk, something happens actually to the scale factor, and this is what indeed leads to this holographic sort of renormalization group, that the farther you go into the bulk, you basically go to lower energy. But then, indeed, the reason why we're excited about this particular framework is because now what we can do, we can put this system at finite temperature, which is a quantum system, and then in the bulk, we're going to find an object, and if you include in the dictionary what happens in the bulk, there is indeed a black hole that precisely would have that particular temperature. So in this way of producing a black hole geometry, we can now do very precise sort of calculations where we can indeed contest this idea that there should be a relationship between the thermodynamic properties of a quantum system and the gravitational properties of a black hole. So again, this is sort of a review of some of the development that sort of led to the sort of more recent discussions of relationships between quantum physics and gravity. The story continues. Indeed, if you ask, well, does the same question or the same sort of paradigm, if you wish, can we apply that not only to black holes, can we also apply it to our own universe? And it's true that, again, since 30 years roughly, we know that we have a positive cosmological constant in our universe. And that means that our universe is accelerating. And if we would wait long enough, basically the dark energy that we have observed in our universe, which is the source of the acceleration, will actually dominate. And so what does it mean if indeed the universe keeps accelerating? It means that essentially the universe also gets an horizon, because if an accelerating universe is expanding in a way that if you look far enough away, there's going to be a point in space that will move away from us with effectively the speed of light, which means that if I try to send a signal to that point, it will not be able to reach beyond that particular distance. So that distance is what we call the horizon, and you can basically compute how far away that distance is. It's roughly 10 to the 15, 15 billion, light years away from us, where if you would try to reach that point with light, eventually light will also hit a horizon. In terms of mathematical equations, it's the equation on top. That thing is known indeed as the Sitter metric, and indeed r is the radial distance from a point, say us on Earth. And then because of the fact that the prefactor of the time component of the metric goes to 0 at a certain radius L, which is the radius of the universe, this thing indeed will have the same essential properties of a black hole, except that we now have sort of inverted things around. Previously, the black hole is something that hopefully we're staying outside of. Again, if your K radius is enough, you want to go inside. But at the same time, in the case of the universe, we don't have a choice. The horizon of the universe is surrounding us. And then if we apply the same principle, and this was done sort of in a paper also by Gibbons and Hawking, essentially derived, that we should be able to associate entropy to the area of an horizon. Indeed, this horizon will have a temperature, and then if we apply the same rules of thermodynamics, this temperature will lead to an entropy that has the same formula as that Hawking had, except that the area now is the cosmological horizon. Now you can plug in the numbers, and then you find that the entropy that we should be associating with the cosmological horizon is actually 10 to the 120. So a certain way of thinking about this, it's telling us that the presence of dark energy implies the existence of a horizon, and it implies that the universe basically has degrees of freedom that account for this much sort of entropy. And therefore, essentially from this point of view, sort of the unknown parts of physics that we have not yet uncovered are sort of characterized by these numbers, because this entropy that we associated with dark energy is not made out of the stuff that we would normally identify as atoms, because indeed they led to a much smaller entropy. So the question is, what is all this entropy? Where is it hiding? And can one actually derive this from a microscopic description of nature? Now, in order to say that we can sort of understand this, again, this is one of the questions that a theory of quantum gravity should be able to answer. And I think also people here at Stanford have sort of made important sort of contributions sort of to the program to devise a theory that can explain the cosmological sort of evolution in a way where we could understand also the quantum mechanics. And I'm going to give you my answer essentially to this question: what would a theory of quantum gravity look like? What really would quantum gravity do for us? The optimistic scenario would be that we actually discover exactly which theory, string theory, would describe our world, and then we can do computations in it, and then we would be able to sort of claim and verify that we have a theory that includes both gravity and the standard model. However, we've discovered within string theory, and I think maybe for good reasons, that there could be possibly many answers to this question. And that answer may not be unique. And the question is, should you at that point just give up and think about other problems? I think it's still important that we indeed want to describe nature in a way where we actually understand the laws. And especially in these days, I think we're hoping to take advantage of the fact that quantum mechanics is a theory that, although it leads to unpredictability from the point of view of doing measurements, so it's only giving us probabilistic interpretations, or at least predictions of what a given measurement might lead to. At the same time, quantum mechanics is an actually completely predictive framework that if I would give you the initial state, say, of your quantum computer, and you start doing a particular computation, you want to be able to know what the final state is. And the same should be true for our theory of nature. So a theory of quantum gravity, in my mind, and it should be, going backwards, forward, should be able to explain the properties of all parts of our universe. And since black holes and the universe itself encode most of the information, that's where most of the challenges are. But we want to be able to do it in a way where time evolution is unitary, and that the total amount of quantum information is preserved. Again, here is an example of a circuit where indeed the final state indeed can be predicted once you know the intermediate steps that you're doing in this quantum computation. But now indeed Hawking sort of made an important point, and I'll be honest, at least when Hawking made this point, when he made his discovery, I was actually sort of annoyed with the way he posed the question, at least when I was later learning about it. Namely, he sort of introduced this question that we nowadays call the black hole information paradox, where he said, hey, if I look at my calculation of how black holes can actually radiate, indeed there's this process essentially where there's pair creation at the horizon, and every time there's a particle being created, there's also an antiparticle essentially going into the horizon, which leads to an increment in entanglement between the exterior and the interior. So it means basically there's more information that sits inside of the black hole because of the particle that falls in. At the same time, the particle that falls in will never be able to escape. It sort of dies at what we call the singularity of the horizon, and therefore quantum gravity sort of inevitably leads to a certain unpredictability, which is on top of the usual unpredictability of sort of the quantum measurement. So essentially the circuit, if you think about it in terms of sort of quantum circuits, again here I'm drawing the thing that I would call a good circuit, where we actually do a computation and we have an equal number of initial input and output data. This is an example of a bad circuit, which is basically where Hawking sort of ended up in thinking sort of how black holes work. Namely that you start with some initial state that could be producing a black hole. This is sort of the formation stage of a black hole. Then there's going to be an intermediate state where the black hole has almost unique state, which is only labeled, say, by 2 qubits. It's mass and angular momentum. And then eventually the black hole will evaporate. It will produce radiation. But then you have to sort of basically say, hey, that radiation is coming from somewhere. Let's introduce some new qubits over here. and then sort of have this mapping from the green to the green, but you've actually lost information along the way. So this is what I would call a bad circuit. Now, I wouldn't even say that currently we have actually solved this problem, but the resolution, at least to some extent, will undoubtedly involve sort of new ideas that sort of have been the focus of attention over the last 10 years as well. But the idea sort of started a little bit earlier. At Hoofd, again, he was my advisor, and when I was a graduate student, and he would be drawing all kinds of pictures about black holes when I would meet him in his office. By the way, he gave me 2 pieces of advice. One was not to work on string theory and not to work on black holes. And I ignored both pieces of advice when I was a graduate student at the time. Although the black hole part, initially I did not think about it at the time because it seemed too hard. But later on, it kind of came still back. But indeed, many of the things that we're discussing now, he already had been thinking about, at least was thinking about them in those days. But one of the main points that he brought up was really the fact that if you think about the black hole horizon, it's still a more mysterious place than you perhaps would have thought. Of course, it was already a surprise that Hawking was able to kind of at least compute that in a quantum theory, one is actually in a situation where you can have particles escape from a horizon, which is, again, surprising because it looks as if you can only escape from a black hole classically if you go faster than the speed of light. But this pair creation process of Hawking kind of partly explained that. But the assumption that Hawking was making is precisely that the horizon actually is a smooth part of space. So if the horizon is smooth, then you need to have this entanglement that leads to the pair creation. And Hoofd was sort of turning this thing upside down. Basically what he was saying is, okay, the way Hawking actually also did the calculation, he said, well, hey, if I want to know what comes out of a black hole, let's take my measurement that I do later and let's see how it translates when I go back in time. And then you actually discover that the condition that you don't have any particles in the future is very different from the condition that you don't have any particles in the past. And therefore, if you impose that there were no particles in the past, you conclude that there were particles in the future. Okay? If you think about Hawking's calculation as basically a prediction from the past to the future, this calculation makes a lot of sense. And indeed, it's clear that there's sort of a relatively mild process going on, which is this Hawking pair creation. And indeed, the temperatures that you get are not huge. But Hoofd sort of made a different point. He said, well, hey, if I make this observation and I look at late times, a Hawking particle that comes out actually had a very high frequency when it came back in time, because a black hole indeed leads to what we call a redshift. But more importantly, what Hoofd pointed out was that if I look at the, let me think if that still works. So it's sort of one of my second laws of thermodynamics. Whenever I have one of these things in my hands, the thing doesn't work. But okay. So when I have this particle, which is the green line that comes out, suppose that it had the plan to indeed to come out at a certain moment in time. But there was an initial perturbation that went inwards. That initial perturbation, which is the red line, will actually have a relatively big consequence for the particle, even though it may lead to an exceedingly small shift, basically because of what we call gravitational back reaction. This thing has a mass. It may be a very tiny mass, but it's going to go into a black hole. I should have mentioned, this thing is, of course, the horizon of the black hole. This is a space-time diagram where indeed nothing can go by more than 45 degrees. So this thing here indeed will make it out. Anything that would be in this region here would actually be in its future would be the singularity, which is this yellow thing here. And basically what happens indeed is that the ingoing particle will delay the arrival of the outgoing particle. And part of the point is the following, is that there is this interaction, which indeed you can look at just as the green line and the red line sort of meeting. But this shift that's taking place here is proportional to the energy of this particle. Let's call this particle here, let's call that B. And the green particle, let's call it A. And that shift leads to what we call an S matrix, and nowadays it's called the 't Hooft S matrix. That tells you that the momentum of this particle will shift the location of that particle by an amount given by G Newton times the momentum. So there's this equation here, this should be a subscript A. That A times B is indeed this particular S matrix times B times A. And indeed, this is what we call the butterfly effect, that the incoming particle will have a large consequence for the trajectory of the outgoing particle. The reason why it's called the butterfly effect is that indeed this small little shift will get exponentially enhanced if you sort of take into account the translation between the coordinate system that takes place that applies to the close to the horizon and the eventual arrival time at infinity. And the best way to see that this exponential factor is there is just imagine that, in fact, that this shift would be such that this particle would be shifted behind the horizon. Then something that would have come out at a finite time actually comes out it never comes out because it sits at the back of behind the horizon. So it's possible that this effect actually leads to dramatic consequences for this particle that we call A. Now, this particular phenomenon, that a small perturbation leads to large consequences, indeed, is indeed typical of what we call chaos. And then precisely this exponential that we have in the previous slide, this exponential is what we would call the Lyapunov behavior. Lyapunov behavior is characteristic of chaotic systems where you have exponential diverging paths. So now if we think about a black hole as a true system that's made out of stuff, then the question is, what does this mean for the stuff that it's made out of? It actually means that whatever the dynamics is that describes a black hole should be chaotic. And this was indeed the major contribution of Schenker and Stanford that sort of pointed out that we should think about black holes indeed as what we call scrambling systems. It's not only that they have a lot of information or entropy, it also means that in terms of their time evolution, it's indeed a scrambling system. And that indeed makes us sort of think about models by which we would like to sort of understand the physics of this scrambling. Let me briefly go back still to the previous slide. So the work of Schenker and Stanford indeed led people to think about what could be an example of such a scrambling system. And this is where the SYK model comes in. So now I'm going to transition essentially from talking about gravity. I'm going to talk about indeed systems that have this particular behavior, that operators can have exponentially large consequences in terms of the time evolution. And these would have to be chaotic systems. So I'm going to turn the question a little bit around, is rather than thinking about the space-time geometry, let's indeed sort of now actually go through the exercise of starting with a quantum system and extracting geometry from it. So this is what I'm hoping to do in the second half, at least, of the talk. So the question is, okay, well, let's imagine indeed a quantum system that's doing something seemingly random. And that's indeed what the Sachdev-Ye-Kitaev model is. So Kitaev indeed identified this model, which was already earlier studied in various parts of the literature, where essentially you can think about it as a quantum algorithm, but a quantum algorithm which has very random properties. So essentially the degrees of freedom are qubits. Again, they're labeled by things we call Majorana fermions. These psi variables, and these are basically qubits. But we have a lot of them. We label that by n. And then we let them interact. So basically you take your quantum circuit, you have a lot of qubits, and every moment in time you let a Hamiltonian act, which is this Hamiltonian. And what this Hamiltonian does, it takes a sampling of those qubits and just flips them randomly with a certain probability that's sort of governed by this number J. And then what happens then over time is that even though, say, the system at a given moment may have been known, rather quickly it will be essentially in a random state. One way of thinking about it is that if I would have a given qubit that sits here, it will actually influence 3 other qubits at a later moment in time. Each of those 3 will also then influence 3 more, and this produces basically a cascade where indeed quantum information spreads enormously quickly. And of course, this effect will become even stronger in the case that the connectivity is actually more sort of high dimensional. Here it's with 4, but in principle you could have even up to p, where p could be a large number of things that are interacting with each other. So when I introduce this particular quantum model, again, it's a random evolution of a Hilbert space, if you wish, from the point of view of sort of time evolution. It seems that a priori this thing should not have much to do with gravity, because again, now I've sort of jumped into the quantum realm. Where is gravity and where is the geometry? Again, work indeed, which is why people got excited about this, is that this thing indeed, when you think about indeed this, what we call this butterfly effect, indeed it has this particular behavior that correlation, if you take sort of the commutator squared, which indeed essentially is comparing BA with AB, you get something that grows exponentially. And indeed, if you do the computation and you sort of think about the operation of acting with an operator A as sending in a particle, or maybe deciding that you want to detect a particle at some later time, if you send in something else with an operator B in this setting, indeed it will basically, because of the random dynamics, have a drastic consequence for the observations that you do on A. And it indeed turns out that if you compute things in this SYK model, you actually find that indeed the effect of sending something in indeed can essentially be described in terms of what I would call this, again, this 't Hooft S matrix, where indeed things are shifting each other. I claim that this is true, and indeed people have done the computation. But it kind of is a bit mysterious. I started with a model, which is this SYK model, which is completely random. But it appears to be, at a certain level, to be still simple and geometric. I could sort of talk more about this. There are many things, by the way, indeed, that I could be talking about that I'm not going to talk about because there's only so much time one has in a colloquium. So what I'm going to do, I'm going to briefly hit a short moment of sort of contemplation, or at least sort of self-reflection, because basically what I'm doing now is I was interested in learning about space and time, and I'm suddenly sort of telling you that I'm studying random quantum systems. So how is it possible that I can start, in the end, still connect with the things that I'm interested in? And at this point, actually, I found it sort of helpful to sort of take a bit of inspiration from also indeed someone who was at Princeton for a long time. And essentially what I'm going to do in the next few slides is to sort of reconnect this sort of more random picture that comes out of SYK with something that's much more geometric. And I'm going to do it maybe in a slightly surprising way. And basically what I'm claiming is that if you take sufficiently random dynamics, that a beautiful mathematical structure will come about. And I'm going to try to explain that. So Wigner, in 1960, wrote indeed a paper where he indeed sort of was grappling with a little bit of the same issue. He was aware, of course, that the laws of physics could be sort of very successful. At the same time, he also knew very well that there are things in nature that look extremely random. If you read the paper, he sort of talks about many sort of points of this about this question. But the fact that mathematics sometimes is remarkably powerful as a way of describing things that a priori should not be describable in terms of beautiful mathematics sort of is what underlies this. And of course, Wigner himself famously kind of had a perfect example of this, where basically what he was doing, he was studying basically something that could be sort of applied to nuclear physics. If you have a nucleus, it's very hard to predict that if you shoot something into it, what's the probability that it will go into another state, or what's the probability that the particle will, that the nucleus will decay into a particular decay product. That's something one cannot really compute from the perspective of solving the Schrödinger equation. So Wigner did something more clever. He said, well, hey, if I still want to learn about nuclear physics, let's indeed start thinking about the ensemble of all possible nuclear theories that I could write down. And he said, okay, well, so the Schrödinger equation is described by a Hamiltonian. So let's think about the energy spectrum of the Hamiltonian. Sorry. And that energy spectrum is discrete. But the fact that I know that the Hamiltonian is an Hermitian operator should actually give me some information. And indeed, if you describe the ensemble of all possible Hamiltonians and you take some potential, which in this case, say, could be even just chosen to be a Gaussian potential, you get sort of an interesting prediction, which Wigner indeed made, which is the semicircle. That in the limit where the energy levels are extremely low, you have extremely many energy levels, physics again becomes very irregular, and the distribution of energy eigenvalues turns into this semicircle. This is one way of thinking about how beautiful mathematics kind of emerges from random underlying physics, that if you take the randomness to be big enough and you take the limit where the randomness essentially is maximal, but also where the number of constituents becomes very large, you again get beautiful geometric properties. And the SYK model is actually came out of partly this development. And indeed what people did in the early 70s, they took Wigner's model, and instead of just having the energy levels, they also allowed the particles to interact with each other. And that interaction between the particles is precisely, takes the same form as this SYK Hamiltonian. And indeed, the emphasis that I should have made in the previous slide when I introduced the SYK Hamiltonian is that the coupling constants of the SYK Hamiltonians are random numbers. And this is going to be quite important for the rest of my discussion. I'm going to skip, in view of the time, the next slide, I think. Because basically, this is trying to answer partly, first of all, where quantum many-body physics, how it connects with string theory, and also why something geometric comes about. But I can return to this slide later on. But maybe the thing that I want to point out is the fact that there's a quantum many-body system that sits over here, and this is what we call the UV theory. And then the geometric description sits over here, where indeed we've taken a large n limit, and we've taken into account the fact that this quantum many-body system is actually very random, and indeed it's called a disorder average. But then what we're hoping to achieve is that by having this quantum system, that this geometric description actually is a form of quantum gravity, and that indeed that the quantum many-body system by itself should be thought of perhaps as dual to a theory that basically explains the origin of gravity. So again, in view of the time, let me indeed get to the sort of the thing that I've been thinking about over the last few years. Basically, if you take the SYK model, it has a very interesting large n limit. And I claim that this large n limit indeed allows us to come back to geometry. So I had a psi in the SYK model, the number of possible psis we call n. I had the Hamiltonian of the SYK model, which had a pth order interaction, so that's the number p. And I'm going to take both numbers fixed, but in a way where p squared divided by n is a constant. And we'll see later why we want to keep this thing fixed. And we take both to infinity. It turns out that the spectrum of this theory is actually quite interesting. It turns out that it's what we call, it's bounded if you take this limit, meaning that the energy can only go over a finite range, which is, at least for maybe for most people that think about quantum mechanics, not such a surprising thing that you can have systems where energy only is bounded over a finite range. I should say, though, that people that study quantum field theory would sort of find this already an unusual spectrum, because typically in quantum field theory, we're expecting to be able to look at arbitrarily short distances, which means that we are allowed to go to arbitrarily high energy. But anyway, this system has this particular property, and the reason why this is actually interesting is that we can study the system not just sort of in a random, in an average situation. We're going to be studying it in a situation where the temperature of the system is going to be sent to infinity. So what does it mean for the temperature to go to infinity? It means actually that you're sitting at the place where the system is most random, or at least most, sort of has the largest entropy as well. And indeed, if this is the spectral density, it means this tells you how many states you have, and it should be compared, say, by the way, with the semicircle law of Wigner. We're going to be sort of studying the system in this limit, and the proposal that Lenny Susskind and Adel Rahman and independently with Nora Vlansky and I, we've sort of been making the suggestion or the proposal that this limit of the SYK model should actually not be thought of as describing a black hole, but it should be thought of as describing de Sitter space. And I think if this is true, then this will be an important step forward because it allows us to essentially start thinking about quantum mechanical systems that don't have necessarily a negative cosmological constant, which is anti-de Sitter. De Sitter is a more realistic example of a geometry that connects with our universe. So if this could be done, it would be a good step forward. And indeed, the proposal, again, comes sort of in two layers. Indeed, there's this parameter that's called lambda, which is the ratio of this p squared over n. If you keep it fixed and finite, but you send n and p to infinity, it's sort of suggestive that this might sort of be associated with a sort of a difference between two energy scales. From the point of view of string theory, you can think about lambda potentially as the string scale. But my point of view, at least the thing that I want to explain in the next 10 minutes. Do I have still 10 minutes? 9. Okay. In the next 9 minutes, is I would like to sort of explain to you how the SYK model leads to something that looks both geometric, and I would like to explain it also in a way where the geometry that it actually leads to is not a geometry of de Sitter space, of anti-de Sitter space, but I'm going to explain to you why it's actually de Sitter. So at least that's the thing I'll do. So I need to, this is going to be maybe the most technical slide that I have. I need to tell you about something that's called the Chord rules. So think about the SYK model indeed as a time evolution where indeed we're acting with the Hamiltonian, and the Hamiltonian is flipping qubits, but it picks a random set of qubits that it wants to flip. And then in the end we're going to sort of compute what we call expectation values, where essentially we want to go back to a situation where the qubits go back to the original situation. So we take the expectation value essentially by taking a trace where everything returns back to itself. So what that means is that if I act with the Hamiltonian at a given moment in time, then the next moment, by the way, there has to be another operator sometime later that looks identical to the one that I acted with at a certain time, where all the qubits that I flipped actually flip back. So what that means is that the combination of the two operations actually is trivial, and the way I'm indicating that is by drawing a line between them. And essentially, if I draw this line, if I draw this diagram over here, then this diagram as a whole will just be 1. Because I flip the spins and then later on I flip them back again. Okay, so this is just equal to 1. And it's true, I could do this many times. I could act with a bunch of these things and then later flip them back again, and all of this is just equal to 1. However, it's possible that one of these operations might actually happen not at the same time, not separately, but that before I actually flip things back, that there's going to be another operation that took place in between. Which means that these lines that are connecting these two are actually crossing. I first do one, then I do the other, then I do the other again, and then so the lines are crossing. And at that point, I'm going to be sensitive to the fact that these things are actually Majorana fermions, and that there's a minus sign that shows up when two things are actually the same, or actually the other way around. If two things are the same, actually they don't give a minus sign. If two things are different, they actually do give a minus sign. And then you basically have to do some counting. You have to basically say, hey, I have two of these operators. What's the probability that they have an overlapping index? And then if you look carefully, they're going to be, if this is p, in this case p is 4, I have 16 points here, which is p squared. The probability that two of these lines actually have the same index is proportional to p squared over n. Right? Because n is the total number of indices, I have p squared indices, and that's the probability. And then if you think about it a little bit more, it turns out that basically that the probability that there's some index the same is Poisson distributed, and then it turns out that each of these crossings that I have on the right, which you can think of as basically a crossing between different instances of acting with the Hamiltonian, leads to a factor that's known, which is this factor q. So therefore, indeed, this is what's called the Chord rule, is that every time you have crossing lines, there's a factor of q. So this comes from combinatorics in SYK. I'll skip this slide maybe. I'll be very quick here. So I have the Chord rule, and I'm going to connect it with geometry on the other side. Since I have 5 minutes. Is that 4? Okay, good. I'll be quick. I'll skip this slide then. So geometry, the geometry that shows up here turns out to be basically that of 2 + 1 dimensional physics. And again, we have Bob Laughlin here. So actually, it turns out that the physics that connects with this thing that I just mentioned with the SYK model is actually that of essentially of the 2 + 1 of the quantum Hall system. So again, there's knot theory, and knot theory is indeed a theory that tells you what happens if you indeed have non-trivial knots. Are they the same or are they not? And that question can be answered by thinking carefully about what happens if you interchange to knots. From one to another. Basically, if you draw a knot, and there are overcrossings and undercrossings, and keeping track of how many over and undercrossings there are can be done by something that's called a skein relation, where an overcrossing, that's over here, I always have the problem, over here, can actually be reformulated as a linear sum of two things where there's no crossing. This relationship, indeed, is known to be a property, indeed, of theories that have fractional statistics or non-abelian statistics. So in non-abelian statistics, precisely we have the same thing, is where we have particles that have trajectories that go forward in space. And those particles, indeed, will, when they move around each other, may pick up a phase. And famously, at least Witten showed that you can actually map this question of what's a knot in 3 dimensions to a computation in quantum field theory, which is known as a Chern-Simons theory. And indeed, there's this identification between knot polynomials and expectation values of Wilson lines. In de Sitter space, it turns out that there's an analog of essentially the same knot invariant. And the thing I'm going to be talking about is indeed how to map this Q parameter that came out of SYK, and it actually turns out to be directly related to the Q parameter that comes out of this knot invariant. So in the case, I should say, of Chern-Simons theory and of the quantum Hall effect, this Q is a phase, and that's sort of the one piece of information that I wanted you to keep track of. Because what will happen later is that the Q parameter that comes out of gravity indeed is a real number, and indeed the Q parameter that came out of the SYK was also real. So what are we doing? So let's immediately go to the lower picture. We're essentially asking about what happens in a theory of gravity if we place a mass at a given point. And if we do that, the mass at a given point in 2+1 gravity will create what we call a conical deficit angle. And essentially it will eliminate seemingly a part of space, but basically it creates a new boundary condition that if you go around, that the angle 2 pi will get reduced by an amount of delta theta, and that delta theta is proportional to the mass. Now, so here's the analogy, is that in the quantum Hall effect, indeed, we kind of know that you can essentially understand the fractional statistics as sort of a generalization, indeed, of the Aharonov-Bohm effect, or an application, if you wish, indeed, through the combination of flux attachment, where if you take a particle with an electric charge, it will actually have a corresponding flux attached to it, effectively, that's proportional to its charge by a number which is 2 pi over k. And that, indeed, if you now take the Aharonov-Bohm effect into account, plugging in this phi to be that q leads indeed to this famous fractional statistics formula. The same happens now in gravity, where going around a conical deficit indeed creates again a phase in the wave function which is now proportional to the angle times the angular momentum. And the gravitational back reaction in that case, where theta is an angle, is now summarized in this formula, where this theta is proportional to the mass. Theta will rotate things, so it's now couples to the angular momentum. So this thing is sort of, you can think about it as a gravitational Aharonov-Bohm effect, or a gravitational fractional statistics. Now, let me make now a comparison between what happens in gravity and how to extract indeed the phase. If you think about it, it turns out that once you add curvature, then there's a definite, 1 minute, okay. Then there's a definite relationship between sort of the generators of space-time symmetries and what we can call charges. If you take the two combinations together, you actually discover that the thing that naturally gives rise to the sort of the gravitational Aharonov-Bohm effect, indeed, in the case of the Sitter space, gives a real parameter q. In the case of anti-de Sitter space, indeed gives a phase vector q. So this thing is actually more like the fractional statistics in the quantum Hall system. This thing is actually more like indeed what I call the Sitter gravity. Long story short, since indeed I only have 1 minute or 30 seconds. By the way, there's one bit of information that at least I want to at least transfer here, is that indeed if you think about the gravitational statistics that follow sort of from gravity, indeed that allows us to distinguish de Sitter and anti-de Sitter gravity by indeed this q parameter. And it turns out that essentially, if you think about the SYK rules, they also give rise to this q parameter. And basically, the fact that SYK has these, what we call these Chord rules with that q parameter, can be used to make a dictionary with 2+1 dimensional gravity. And the 2+1 dimensional gravity is that of the Sitter space. In the last 0 seconds, let me indeed mention one particular consequence of how we might be able to sort of test these ideas. So these ideas, again, Susskind, at least a couple of years ago, started thinking about this connection between SYK and de Sitter. I came from a different angle. We've been talking over the last few weeks, and I think we basically agree that we agree on how the physics should work. If this can be sort of realized, I think it will give us a new way of thinking about sort of connections between gravity and quantum many-body physics. Many thoughts that people have sort of developed along these lines typically connect black hole physics with quantum many-body physics in sort of interesting ways. In this case, in the Sitter space, there's a new way of thinking about it. And it turns out that these shock waves that I was talking about earlier, indeed in the zeta space, behave in a more interesting way, or at least in a different way that's interesting. So if I'm sitting at the north pole of the zeta universe, there's someone sitting at the south pole that I cannot communicate with. So if I send a signal, my signal will never reach that person on the other side because we're accelerating away from each other. One of the nice and surprising things, perhaps, is that if you take into account the same shock waves that I talked about earlier, that Hooft was pointing out, then it turns out that if you send the signals, the North Pole and the South Pole person send the signal at the same time, then it turns out that because of gravity, that the two signals actually can reach the other side. So if we would sort of now make a mapping between the zeta space and this SYK model, one thing one should be able to verify, at least according to this duality, is that it's now possible to take indeed these two sides of the system, allow them to send signals at the same time. In that case, they can communicate. However, if one of them would only send the signal, then they would not be able to send the signal to the other side. I will stop here. Again, there are some conclusions. Thank you for your attention.
Thanks, Herman, very much. I have some questions.
I'll start. So, lots of us are interested in what the stuff is that makes up space. And after you've thought it up, you got an idea. Then we need an experimental test. This particular one you've described is a pretty long distance experiment. And
you mean the last one? Yeah.
One, and I think I understood what it was. It was basically a modification quantum mechanics, I think. But anyway, maybe I didn't understand. But is that it? I mean, is there
tests?
Anything else beyond traditional gravitational between general relativity?
Right.
Are going to measure and find something different?
Right. No, so that's of course a good question, and I had to lunch this afternoon with postdocs and graduate students, and we're asking the same question. So what would be an experimental sort of prediction for this? So I would say, so in the case of black holes, indeed, and I use it as an important motivation because it's guiding a lot of the thinking. And indeed, up to now, thinking about these kind of ways of modeling the stuff that the universe is made up from in the context of the zeta space is only sort of beginning to be explored. But I think there are going to be important questions. So one puzzle is the following, is that if you think about our universe, again, we have the horizon problem, basically, if you think about the Big Bang. In the case of when we go back to a very early universe, it can no longer be maintained that gravity and quantum mechanics really remain separate. Because indeed, once we get very close to the Big Bang, it's not just that things get hot, it's also that things have to become very non-local, because things over there look the same as things over there. So if we have a quantum mechanical model of a cosmological time evolution, then we can basically start testing some of these ideas. And for example, currently our claim, at least our best understanding of the thing that leads to fluctuations in our universe, is that they started out as quantum fluctuations, right? And if we would be able to sort of build a theoretical model where we can literally follow the quantum time evolution and match that with observations that we see from the Big Bang, I think that would really be a place where there's much more hope for an actual experimental test or an exponential prediction. In the case of black holes, one needs to be more optimistic if one would want to sort of come up with a prediction from quantum gravity. But in the case of the early universe, I think there are many reasons to think that the two things will provide sort of new insights.
I have a question. So usually when we think about horizon, that means there is a border like beyond which I cannot see. But what you just discussed in the previous slide is in this de Sitter space, actually there is a way to see beyond the horizon if somebody happens to send a signal
at the same time.
So does that mean the horizon itself is just not well defined, or at least not stable?
No, so what's the notion of indeed a horizon? Indeed, that's a good question. Yeah. So what the notion of a horizon really is indeed where if you take just classical propagation on a given space-time, that you can sort of not go beyond it. And initially, indeed, in the previous slide, if you take this setting, then it looks actually pretty sort of conclusive that someone far away from me is actually moving faster than the speed of light. So I should not be able to send a signal to that person. So it's indeed a relatively dramatic effect that somehow the fact that in de Sitter space it turns out that these shock waves work in the opposite direction, and essentially what happens is that the universe gives itself more time, so it stretches out. And then at that point, the notion of a horizon is no longer, at least including back reaction, is no longer sort of a precise mathematical notion. I would say, so the test that you would have here would be two-way communication is possible, but the thing you would like to be able to show is that one-way communication is literally then impossible. Which means that if only the person from one side tries to send a signal to the other side, then there should be no communication possible. So that would still be a precise definition, I would say, of an horizon. Because in that case, again, you don't have this collision that opens up the gap.
Any other question? Yeah.
So this SYK model with this kind of scaling p squared proportional to n, it kind of makes me want to visualize a two-dimensional system with interactions along some like one-dimensional curve. Is that a useful picture, or is that insufficiently random to build this kind of model?
It's a good question. So geometrically, indeed, as you said, simply the fact that if you have and it's true that it would be natural to think p as roughly the square root of n, or n as indeed literally the square of p. Yeah, I think geometrically one way in which one could sort of potentially sort of scale things up so that you're in this situation would be the way you're describing it. And it's true that by the way, that again, things that sort of have a combinatoric definition from the point of view of the from the SYK model. So a priori, I should say, the SYK variables are just sitting in some abstract space. They're labeled by I. They're not physically sitting at certain locations. If you want to make it in a lab, then you would put them physically at certain locations. But indeed, it might actually be helpful to think about sort of the geometric way of realizing indeed this.
It's maybe related also to just how, do I need all possible combinations of the IJKL?
Right. Right. I should say that the SYK model is probably a class of a much more general set of models. One can do more interesting things by going to a next layer of complexity, at least in terms of building the model. But the it has to be necessary to have it scrambling, which means that you have to have everyone talk to everyone else, but maybe not at the same time. And that's what this P is labeling.
So you referred to the holographic duality at the start, and you did this comparison going between SYK and 3D de Sitter. And SYK is 1 plus 0 dimensional theory,
right?
And then 3D de Sitter is not a 1 plus 1 dimensional theory. So what's the deal there? Why can you go from?
Yeah, right. So that sounds like a relatively drastic step. And if you notice one thing, it is true that most of the physics that one is extracting maybe is not quite sensitive to the sort of the angular momentum in the third direction. But let me still make one point, and that's sort of a crucial one. Anita, I talked about the knot theory and the braiding. That's already kind of a bit of a surprise, is that how can you actually think about, you can only sort of do knot theory in 3 dimensions, you cannot do knot theory 2 dimensions. And the way this works is that if you think about sort of what organizes in SYK, sort of the structure is indeed what I was mentioning. It's where you have one Hamiltonian acting at a later time, canceling out with a Hamiltonian acting at an earlier time. So there's actually a line between them. And then indeed, as I explained, once you have sort of 2 of these things, then I can sort of link them by putting a similar pair, but then with one of them in between. So that was the situation that I was describing. It's the AB-AB situation. And then you can indeed ask, okay, well, is there indeed sort of an overcrossing and an undercrossing? At that point, these become operators. And it turns out that at that point, you have to sort of talk about the 3-dimensional situation. And indeed, if you look at the formulas that people produce from double-scaled SYK, they look 3-dimensional. In the end, though, one should still think about it indeed as potentially just 2-dimensional. And let me make one other comment, is that in the case of ADS-CFT, we're sitting outside of the gravitational system. So if I have a 2 + 1 dimensional system, I necessarily need a boundary that's 1 + 1 dimensional. In the Sitter space, we're sitting actually in the center. At least we cannot sit outside of the horizon. The horizon sits around. So what you have to think about in this case as the 1-dimensional SYK model as just sitting at the center. And all the observations that you're doing in the quantum mechanics, which is just 1-dimensional, describe basically what happens if I send out a signal and I return it later on. So basically this SYK model, if you wish, lives on a world line, a 1-dimensional world line, but it's surrounded indeed by the environment that provides both the quantum model for the expanding universe and indeed it has a horizon that surrounds it. So rather than sitting outside of the system, you're now sitting in the middle of it. By the way, this is the reason why people found it hard to make the step towards the Sitter space.
Okay, so I guess considering the time, we probably can leave more discussions to the reception. I forgot to mention that Herman will be here until next Tuesday, 27th, and his office is in 324 Variant. Feel free to reach Herman or reach me if you're interested in discussing more. Okay, let's thank Herman again.
Thank you.
Yeah, I think it's helpful to have the introduction.